Okay. Yeah, I'm not exactly sure what happened. So there was a point where I could see you guys, and I asked you questions, and you totally ignored me because I thought you were pulling a prank. And then all of a sudden it seemed like every time you tried to touch the speaker, then we lost each other. So glad we're connected again. But anyways, yesterday we started Chapter 2. We're still on Chapter 2. I'm hoping to wrap it up today. It's probably going to bleed into tomorrow now. We'll start the lab tomorrow. It will probably go into Monday, so that's fine. But we left off talking about electronegativities of elements and how some elements... What do you say? Say that again.
Are you talking to us?
Did you say something?
Yeah, well, okay, we actually have a question.
Sure.
When is this Chapter 2 guided notes due? Because we just got it today.
Yeah, so we're not going to finish the chapter. Let's just say Monday now. Is that good? Okay.
Yeah.
Any other questions?
Nope.
Okay. So electronegativities of elements. Some elements have a higher attractive force. And so you see that pattern as you move across the period or the row, it increases. And as you go down the column or the group, it decreases. So fluorine, oxygen, chlorine have the greatest kind of attractive force on electrons. So when they form bonds, they usually hog the electrons. The electrons hang out with them more. So there are two types of covalent bonds, polar and nonpolar covalent bonds. Nonpolar means that electrons are being shared equally. Polar means that they're being shared, but it's being shared unequally. And you'd have to look at the electronegativities of the elements to figure out where those electrons are hanging out with. Yesterday there was a question about carbon and silicon and if they have the ability to form ionic bonds. I looked it up. No, they always form covalent bonds. Okay, yeah. But electrons are more likely found near atom with the greater electronegativity value, and partial charges are usually symbolized by a lowercase Greek letter delta. So like what happens with hydrogen chloride, HCl, the electronegativity value of chlorine is 3.0 and oxygen is 2.1. They share their electrons because remember hydrogen has, well, that was a really bad age. Hydrogen has 1 valence electron. Chlorine has 7, so they will share, but this electron will be hanging out with chlorine more than it does with hydrogen. And as a result, you get a partial charge. So if chlorine has more electrons than protons, it will have a slightly negative charge. And hydrogen kind of lost its electron, but it still has 1 proton, so it will have a slightly positive charge. And so now you've created a molecule or a compound that has a positive end and a negative end. It's a polar molecule. It's a unique property that we're going to look at in water.
So the EN, that was the chart.
Yes. Okay. So chemical reactions alter bonds. Basically, you're shifting atoms around to, get a full valence shell, and all you're doing is just forming bonds so everyone's kind of happy. You're not getting rid of elements. You're not creating new elements. You're using what you got and just rearranging it. So here I have the famous, does anyone recognize that equation? Photosynthesis. It's photosynthesis. 6 molecules of CO2 plus 6 molecules of water with a little bit of sunlight forms your glucose C6H12O6 plus 6 molecules of oxygen. And so what you're doing is you're just rearranging the atoms and forming new products. But you can do the inventory. You can count how many you have on each side, and it has to be the same. So this 6 kind of, what do you guys call it, foil? Yeah? Distributes, okay. So this 6 times 1 is 6. So if I were to count my carbons, I have 6 carbons on this side. 6 times 1, but there's 2, so 6 times 2 is 12, okay. 6 times 2 for hydrogen is 12. But then this 6 times 1 is 6, so I have to add 6. So I have 6 carbon, 18 oxygen, and 12 hydrogen. So then when I do the inventory over here, how many carbons do you see? 6. Okay. I counted my oxygen next. So 6, and then plus 6 times 2 is 18, and then hydrogen is 12. So you can see that they are balanced. I just rearranged them. 3 factors that influence chemical reactions, and they are temperature. When you heat substances, the kinetic energy, kinetic motion of those atoms move faster, and as a result, they collide. And when they collide and meet, it's more likely a chemical reaction will take place.
Anika Jackson Walker, please come to the office. Anika Jackson Walker.
Second factor is concentration of reactants and products, where reactions proceed more quickly with more reactants available, which just makes sense, because reactants are what go into a chemical equation, or chemical, reaction, and products come out of it. More products tend to slow the reaction, and reversible reactions may speed up. So, Catalysts, a substance that increases the rate of reaction but does not partake in the product. Enzymes are the greatest catalyst. So, in fact, I think next week we'll look at an enzyme lab with liver, and how liver has some enzymes that break down hydrogen peroxide, which is deadly, into water and CO2 gas. So you're going to look at the liver lab with that. But these catalysts, they're not involved in the chemical equation at all. So like, for example, maybe I'll go back to my photosynthesis equation. So there are a bunch of enzymes involved in the process of photosynthesis, but they're not listed in the chemical equation at all. What they do is, they might take CO2 and they might take water and put them together so that way the chemical reaction takes place, thus rearranging it to glucose and oxygen. So, they're just kind of like chaperones. They just like matchmakers, make sure they meet so the chemical reaction can take place. Okay, moving on to properties of water, which is a vital compound. So obviously, beginning of life, water provided a medium for these molecules to move around and to interact. And life evolved in the water first 2 billion years before spread into land. Life is obviously tied to water. Most organisms, actually, I would say almost all, have about 2/3 water in them, and we require a water-rich environment either internally or externally for growth and reproduction. So looking at the structure of a water molecule, it's H2O. It has single covalent bonds. So covalent means that it's sharing electrons. But what do you notice about the diagram with the sharing of electrons?
It has the little Greek symbol.
It's got the little Greek symbols, the delta minus and the delta negative. So what does this delta negative symbol mean?
It's sharing. Well, it has one more or more electrons.
Oxygen,
Right, so
water,
oxygen's pulling more electrons towards it than it is for the hydrogen. So then as a result, hydrogen has positive ends. Now, if I were to stick another water molecule right next to it, well, it's kind of like a magnet. Opposites attract. And so this oxygen atom will be attracted to other water molecules, but the hydrogen ends. Water is a very stable molecule. There's no unpaired electrons or any net electrical charge, but it does have a slight dipole moment that allows it to have special properties.
So this would be like a polar.
Yes, this is a polar
bond.
molecule. So because of these slight charges, the slight dipoles, it can form something called hydrogen bonds. Weak chemical associations between other water molecules. The partial negative charge on the O and the partial positive charge on the hydrogen. It's very weak, 5 to 10% strength of a covalent bond, but it is responsible for the many properties that are needed for life. And so we will look at those properties. The partial charge causes water molecules to be bent, kind of like that V shape that you saw in the previous diagram.
Does this have anything to do with like why water is like a liquid this time?
Yes. Absolutely. Everything to do with it. So water molecules are cohesive. The word cohesive means that it will stick to itself. So it will stick to other water molecules. So the polarity of water allows water molecules to be attracted to one another. This is the reason why water is a liquid at different, like moderate temperatures, I should say. And it's also responsible for surface tension. So if you've ever seen water striders kind of gliding on the surface of water, that's surface tension, the tautness of the surface of a liquid. And so what's going on here is that we have these hydrogen bonds associated with a bunch of other water molecules. And it's just strong enough to hold light things. Last year in biology, did Rourke ever make paper clips float? No? Okay.
I think you did for our bio.
Yes, I did for your bio.
Or
Or,
you did.
I mean, oh, he did for your section?
Did
I think I did it in life science. So if I had you for life science, you may have seen it. So these are all polar molecules interacting with each other, and you can disrupt the surface tension by introducing a non-polar substance. So this is really mean, and I would not recommend it. But let's just say that you have a water strider in a bucket, an ice cream bucket, and it's just gliding around, almost like it's just ice skating, but it's liquid water. But you could drown it if you really wanted it to, All you'd have to do is take a drop of soap, and I kid you not, just barely touch the water, and the surface tension, it will interact with the hydrogen bonds and kind of break it, and then the water strider will fall through. So I didn't do it with water striders, that's me. I did it with paper clips. I made paper clips float, and then I just took a toothpick and just put a little dab of soap, touch the surface, everything just sank. It's actually really cool. You'll see it in your water properties lab tomorrow. So let's go there. So yeah. Okay, another property of water with the polarity of it is adhesiveness. Okay, so not only does water molecules they stick to themselves, but they like to stick to other polar molecules. So they are attracted to other polar molecules because they have charges as well. So this explains why substances containing polar molecules get wet when immersed. Oh no, I don't want to go back to that question. Is water wet?
Uh-oh.
Adhesion is responsible for capillary action. So if this is a capillary tube or even a test tube or a graduated cylinder and you fill it up with water, you will see something called the meniscus. What's going on there? Well, water molecules are actually clinging to the sides of this container, and they're kind of trying to crawl up, and as a result, it pulls out from the middle, and so you get this nice little U-shaped meniscus. So that's why whenever you measure water, let's just say you needed 70 mils of water, you go to the bottom of the meniscus, not to the top of where it's climbing up the walls. Cohesion and adhesion are really important for plants. This is how This is how plants move water through their vascular system, all because of capillary action and cohesion. Okay, another property of water is that it has high specific heat values as well as high heat evaporation. This is why it takes a lot of energy to boil water, because you gotta pull those water molecules away from each other and then undergo that phase change. This is another reason why ice floats. So it's less dense in the solid form because they arrange themselves kind of in a crystallated structure. It's like microscopic air bubbles, if you will. And it floats on the water. So it's kind of cool. Acts as a solvent for polar molecules. Again, another super important property. Water is kind of like universal solvent. Give it enough time, it will dissolve things. You have water in you. You're made up of 60, 70% water. And the cough medicine you take if you get sick or any type of medicine has to be polar as well. Because otherwise it's not going to mix and get into your bloodstream and go where it needs to go. So it's really important that cough syrup or any medication you take has to dissolve into the bloodstream. Okay. Water can also dissociate to form ions as well. So water molecules, they can be bonded to itself, but then they can break away and become just hydrogen ions and oxygen ions and then reform together again. So looking at the high specific heat that maintains temperature. So I put the definition of specific heat up here. The amount of heat that must be absorbed or lost by 1 gram of the substance to change its temperature by 1 degrees Celsius. So again, large amounts of energy to break the many hydrogen bonds found in that liquid to turn it into a gas. Heats up more slowly, but it can also hold its temperature longer. So this is why sometimes during the day, let's say you go to the beach, the sand is hot, you get in the water, water's cold. But then at night, let's say you go swimming at night. Well, it's cold on land, but then you get in the water and it feels warmer. Well, that's because it can retain heat for longer periods of time. We use water a lot to kind of like insulate heat or absorb heat, become a heat sink in certain processes. So to compare specific heat capacities with water and other substances, here's water, pretty high. Here's ethanol, hexane, propane, granite, copper, mercury. Those two are metals. Doesn't take a lot of heat energy to heat them up. Water, it does. High heat evaporation facilitates coolant. So I put the definition of heat evaporation: the amount of energy required to change 1 gram of a substance from a liquid to a gas. 586 calories for water to change from liquid to gas. So you need a lot of input of energy, therefore, before evaporation can take place. Okay, I already mentioned this. Solid water is less dense than liquid water, and I like this diagram because it shows the crystallated structure, as you can see here. And then water as a liquid just flowing freely, but still in contact with each other. So there's just enough space, allows ice to be less dense, thus floating. So it's pretty important, especially in Minnesota, that ice floats, because if it didn't, our lakes would freeze from the bottom up, and then it would, kill everything. Yeah.
Why is the warm water on top of the cold water?
Mm-hmm.
Is that why it's in condition?
Oh, I'm so glad you mentioned that. So warm water, as you can see, is less dense than cold water. Cold water will sink, and it has everything to do with motion of kinetic energy, so there's more space here. Cold water is more dense, so it's compact. It's because it's getting ready to go into that solid phase, possibly. Yep, so maybe in elementary you had a science teacher or even a teacher heat up some, water and then had some cold water and they dyed it blue and orange or blue and red. And then they slowly poured it in and you could see the blue sank to the bottom and the red was lifted up.
We didn't do any of that cool stuff.
Oh, okay. We'll do that. We'll do that. Okay, so I'm gonna make a note.
Not too expensive.
It's too expensive. One type of
That's what I said. Not a
water and dye.
Although I ran out of blue dye.
Oh.
So, okay, just a quick story. I know it doesn't really pertain. Okay, so I was doing a demonstration for my life science kids. All I did was take green dye, just a drop of it, and then I added a couple drops of bleach, and the green turned into like yellow/clear. So then I'm like, how can we test what's going on here? So then we took yellow and blue dye and put it in a separate beaker. And like tried to mix to make green and then add bleach to see if maybe the bleach was interacting with the green dye or maybe it was interacting with parts of the green dye like yellow or blue. Did I lose you guys?
Yeah.
Yeah.
I kind of get what you're saying. Because you want to see which color will stay.
Right, okay, maybe I'll draw a picture because this is actually kind of cool. Okay, so green dye, add bleach, turns into yellow clear. So I was like, what's going on here? So then I took a beaker and I just had yellow, and I took a beaker that just had blue, and then I took a beaker that had yellow and blue. So then I added it to see what would happen. Okay, and I realized that it only interacted with the blue component, not the yellow component. So
that's why it turns yellow.
right, because then I just did it again to make green, and it did change for this because that blue component was also in there. So blue dye is actually found in green dye. But to make a long story short, I didn't have any blue dye, so I thought I could use bromethyl blue, which is a dye that you would use to stain your cheek cells. It can also be used as a pH indicator, which we can do next week. But it didn't work. Like, all of my results turned out to be negative. So then I actually had to go into, don't you dare tell Mrs. Oakes this. I swear. So I broke into her cabinet, and I took her food coloring dye, and I used 3 drops of her blue dye, and then I put it back. So, no, mom's the word over there, okay? Yeah. So, okay, moving on. Yeah, the kids were like, just ask other teachers. And I'm like, what teacher's gonna have blue food color dye? And one's like, Mrs. Oakes. And I'm like, oh, you're a genius. Okay, I'll be right back. Okay. The solvent properties of water help move ions and polar molecules. So water has this kind of electrical charge, and it can separate other things like sugar crystals, kind of interacts with the OH component and dissolves. So when you dissolve things in water, the water is the solvent, and the thing that's being dissolved is the solute. Okay? And I think that might be a question on your lab tomorrow. So what's going on here? Here's a salt crystal, and you can see my sodium and chlorine ions arranged in a nice little crystal structure. Bye. Sorry. I mean, not finished today. But here's my sodium ion, and you can see that it has a positive charge, and it's attracted to the oxygens. And then the chlorine has a negative charge, and it's attracted to the hydrogens. Thus, salt will dissolve because it's interacting with the polar ends of the water molecule. So this is why things dissolve. If it doesn't dissolve, it means it doesn't have a charge and it's not interacting. So this is why water and oil don't mix. Because oil is nonpolar, has no charges, and just won't interact with the charges. Which leads me to this.
Will the senior homecoming candidates please come to the office at this time for a picture? Senior homecoming candidates, please come to the office at this time for a picture. Thank you.
Okay, so water organizes nonpolar molecules. Your cells are made up of a cell membrane. Okay? All cells have a cell membrane, some type of barrier, and it's made of nonpolar substances. So it doesn't mix with water. There's a barrier, even though there's water inside the cell, so it can help regulate osmotic balances within. So just keep that in mind. But nonpolar molecules don't form hydrogen bonds. They will not mix or dissolve in it. And so we call this hydrophobic. They are scared of water. Polar molecules, they love other things that are polar, aka water, so we call them hydrophilic. Philic means to love. So oils, fats, grease, they undergo hydrophobic exclusion. So they won't mix with water. Instead, they'll aggregate. So I really like the car wash here in Wheaton, especially when you get like the deluxe, the special with everything. And my favorite part is when they spray on the wax, because you can just see all the water molecules beat up. It's just so cool. It's like it looks like this before, then here comes the wax, and then just like, and then you go through the dryer, and it just rolls those blobs of water right off your car. Although I went through the car wash yesterday, and one of the nozzles must have been plugged. So there was a I kid you not, like a stripe of dirt, like right on my it's bad. I don't like it. So don't go to the car wash until it's fixed. Oh, don't talk to me. Okay, I don't know what's going on there. But yeah, wax, pretty cool. Okay, water can form ions. Covalent bonds of water sometimes break spontaneously. So they they're like this. They can be bent, but then sometimes they just dissociate like this with no bonds, and then they'll reform bonds, and then they'll dissociate, and so on and so forth. So water has this amazing ability to do that. So it says water at 25 degrees Celsius, 1 out of every 550 million water molecules will spontaneously break. Reform.
How come we don't see it?
So small. Okay, the last section here. Maybe I might finish today. I don't know. Got 9 slides left here. Acids and bases. So we will do a pH lab next week that is tied into enzyme activity. So keep that in mind. But acids and bases, and you'll learn this in chemistry. The concentration of hydrogen ions leads to how acidic it will be. So if you have a lot of H plus ions, it will be more acidic. If you have a lot of hydroxide ions, which is OH, the more hydroxide ions you have, the more basic you will be. We have something called the pH scale, which is a scale from 0 to 14. Okay? I'm going to say that again, 0 to 14, because that might be a test question. Okay? 0 to 14, where 7 is neutral. And if you have more hydrogen ions, you are acidic. If your hydrogen ions go down, you are more basic. Or you could say, OH high over here and OH low over here. So it's kind of like a seesaw. Whoa. It will pick you up.
Wait, more hydrogen levels
Really?
is more acidic?
What?
Did you say more hydrogen levels is more acidic?
Yes, or H plus.
Acids and bases sucked in chemistry.
Say that again.
Acids and bases sucked in chemistry.
Yeah, and it's taught at the it's literally the last chapter you cover in the school year. So then as a teacher, you're just rushing through it, and then you have to do all these logarithms. It's not a fun.
I wasn't even here for like the first half of it, and then mom still made me take the test.
Yeah, I'm sorry. So water is a not completely stable molecule. I know I just said earlier that it is stable, but it can undergo a chemical reaction with themselves. So I just said that it can split into ions, dissociate, right? Oh, geez, H plus. Water can make things more acidic, but it's really a neutral molecule. Okay, a hydrogen ion is simply a proton. H plus is just a proton because it just has one proton. No neutrons, no electron. Substances that give up protons during chemical reactions are called acids. Molecules or ions that acquire those protons, accept them, are bases. And so a lot of times in chemical reactions you get something called an acid-base reaction or redox. Reactions going on here, but it's the hydrogen that's being transferred. So in reality, protons never really exist by themselves. So like again with water molecule can interact with a water molecule and form a hydronium ion. This is actually an acid, and this is a base. So here I have two neutral molecules, and they can undergo a chemical reaction where one of these gets transferred to get H3O plus and hydroxide ion, which is a base. But you notice that the arrows go both ways? So this is reversible. It can give back that hydrogen and reform water.
Nolan, Frisch, please
Is that
come to the office. Nolan,
H3O
Frisch.
plus on top of the equation? Like, is that part of it?
Yes, I just wrote out hydronium ion. That's what hydronium looks like, H3O plus. So what the pH scale is really looking at is hydrogen ion concentration. That's why I mentioned hydrogen first, and then I mentioned hydroxide. Because pH stands for power of hydrogen. It's looking at the concentration of hydrogen ions. So it's defined as a negative logarithm of hydrogen ion concentration. Pure water is neutral because you have the same amount of hydrogen ions and hydroxide. Like I said, the scale is 1 to 14. Anything less than 7 is acidic, more than 7 is basic. It's logarithmic, so you can figure out like the pH of something, but then realize that the pH of 4 is completely different from the pH of 5. It's not just like one difference, it's the power of 10. So a pH of 5 is pH of 4 has 10 times the amount of hydrogen concentration of a solution with a pH of 5. So then, so between these two, it's 10 times. But then let's say I was comparing the solution of 5 to 3. How many times would that be?
20. 100.
100.
Yeah.
So it'd be 100 times. Oops. Sorry. 100 times.
Is that an exponential function?
Yes. Okay. Acids and bases, some properties. Okay, so anything that increases hydrogen ions is an acid. The stronger the acid, the more H ions are produced, the lower your pH. Stomach acid's a great example of it. Bases combine with H plus ions, thus lowering the concentration of hydrogen ions. Anything above 7 is basic. You can also use the word alkaline to describe bases. So if you hear the word alkaline, it's a base. Cleaning substances like ammonia and bleach and sodium hydroxide, those are all examples of bases. There's a statistic out there that says like 67 or 62% of college students, incoming college students, can give you examples of acids. They're easy. You can say stomach acid, battery acid, whatever, the list goes on, okay? But then they're like, okay, give me an example of a base, and they're like, what? Think cleaning products, okay? So. All right. Buffers help stabilize pH levels in systems. Living cells try to stay close to 7, okay, because enzymes are extremely sensitive to pH. So in your lab next week, you're going to look at an enzyme that's found in liver, and you're going to subject it to different pH levels to see which pH is optimal, okay? What's happening here is that the pH level, okay, alters the shape and function of enzymes. And so when we talk about proteins, we're going to look at how proteins can fold and change shapes when their environment changes. So as a result, you change the shape, the enzyme doesn't work properly anymore. They might be useless, I don't know, and then they don't work. Chemical reactions produce acids and bases, and organisms eat substances that are acidic or basic. So it's really important that we have buffers inside our system that help us keep, us around 7.
Is
So
that why you're not supposed to drink a lot of bleach?
yeah, okay. Definition of a buffer: a substance that resists changes to pH. So what's going on here? It releases hydrogen ions when a base is added, or it absorbs hydrogen ions when an acid is added. It has the ability to do both. We have lots of buffer systems inside of our body, especially in our blood. And so hydrogen carbonate is one. We have some proteins, some hemoglobin, hydrogen phosphate, I believe is what that's called. But all of these work to keep our body around 7 as a pH level.
May I have your attention for today's announcements, please? The Jersey auction is today, so bring your money to bid.
When's that at?
Seniors, if you're applying to a Minnesota college soon,
Yeah,
you may
but
be
like
able
what
to
time?
save the $20
9:15.
application fee by holding on to your application
I
for
know,
a few
I got
weeks.
3 slides here,
Talk
2
to Mrs.
slides.
Zernitsky or Mrs. Young for details. If you are planning to visit a post-secondary school, September and early October are the best times to schedule those visits. Mrs. Young and Mrs. Zernitsky for your advanced
Okay,
makeup work.
yeah, because then we can just start the lab tomorrow and just hit the ground running.
Anyone enrolled on the job must have their interviews complete by Friday morning at 8:15. Juniors will have a prep for the ASVAB in the auditorium on Monday morning at 9:20.
Oh.
Reminder to teachers to put lunch count in JMC first hour. There will be a junior high knowledge bowl meeting Friday morning during break. Seniors, if you would like to submit an application
Did they say
for the
senior high or
zero student of the State Scholarship,
Oh, I was not
please
listening.
see Mrs. Young. Applications are due by September 20th. And the homecoming shirt order forms are in the office. They are due back on Tuesday. And with Dylan Christmas, please stop in the office.
Okay,
Thank you.
so going back to chemical evolution hypothesis and water's role, water has this unusual structure and property that gives it the environment, the perfect environment for chemical evolution to take place. Earth cooled, rain condensed, form in our oceans. Surface is dominated by liquid water. Rain, wind, eroded rocks, dissolving ions to the oceans, and as a result, chemical reactions could take place in water. And so then this last slide here, the environment from which the chemical evolution proceeded was a salty solution of nearly neutral pH. Contains some compounds that could reduce carbon atoms, form redox solutions in the atmosphere. And again, because water has high specific heat, it's a good thing we have liquid water, because otherwise it would just evaporate into space or just freeze and never melt. Okay, so we're at the perfect temperature for water to be liquid, and it's just a good thing that it takes a lot of energy to turn it into a gas. Woo! Oh crap! One more slide. Dang. So in order for the chemical evolution to occur, 2 things have to happen: reactions and small, simple organic compounds, which we'll talk about in Chapter 3, were the building blocks for those larger molecules found in living cells. Those building blocks had to link together to form proteins, nucleic acids, and carbs. Again, we will talk about those macromolecules next week. So the jump from non-life to life had to happen as these molecules begin to accumulate in the waters of the ancient Earth. Okay.